Welcome everyone. So we will be discussing Indian contribution to science. This is a book which is compiled by Vigyan Bharati, and this is one of the chapters which is there for the VVM examination. Chapter 2, Astronomy in India. The beginnings of Indian astronomy. And that is indeed how the story of astronomy always begins. In India, those beginnings are not adequately documented. The first astronomical object found in Andamans belonged to the Paleolithic era, some 12,000 years ago. They are calendar sticks, nothing the waxing and waning of the moon by incision daily notches on a wooden stick. So this is one of the calendar stick found in Andaman's Islands, apparently recording the lunar phases across the several months. Okay, so the apparent increase, that's waxing, and decrease means waning of the moon's disk from new moon to full moon and back in the course of lunar month. So here you see that there are some of the rings stone found at Mohenjo-daro with rows of small drilled holes that appears to the point to the sunset across here. So your patterns of rock arts found in Kashmir, such as double sun or concentric circles, have convinced some scholars that they were depictions of supernova and meteor showers respectively, perhaps witnessed some 7,000 years ago. Ringstone found at Mohenjo-daro, the largest city of Indus civilization 2600 to 1900 BC, which exhibits rows of small drilled holes, have been interpreted as calendrical devices keeping track of the sunrise at different times of the year. The perfect east west alignment of the streets in the same city has attributed to the sighting of the star cluster, which is Pleiades, which is Kritika, which, while the above statement remain speculative, it is well recognized that ancient people everywhere felt a need to relate to the universe by turning into the rhythms of the celestial objects. A few thousand years ago, the Rig Veda, the oldest of the four Vedas, spoke of a year of 360 days divided into 12 equal parts and used a 5-year yuga, which is era, probably as the first attempt to reconcile the lunar and solar years by the addition of a month after those 5 years. It clearly recorded a solar eclipse, although in a metaphorical language, and it has recently been proposed that its mention of 3,339 gods was actually reference to the 18-year cycle of eclipse known as the Sirods. If so, this point to a very early tradition of astronomical observation. A few centuries later, the Yajurveda considered a lunar year of 354 days and a solar year of 365 days and divided the year into six ritus or seasons of 2 months each. The Yajurveda also gave the first list of 27 nakshatras or lunar mansions, that is, constellations, along the path of the moon on the celestial spheres. Because of the need to keep time for the proper conduct of rituals, calendrical astronomy grew more sophisticated in the late Vedic period, with the Vedanga Jyotisha of Lagada as its representative text, and if we call it so, the first extant Indian scientific test. On the basis of its own astronomical data, it has been dated between 12th and 14th centuries BCE by most scholars. The length of the sidereal day, that is, the time taken by the earth to complete one revolution with respect to the given star it uses, is 23 hours 56 minutes and 4.6 seconds, while the correct value is 23 hours 56 minutes and 4.091 seconds. The tiny difference is an indication of the precision reached at the early age. The Vedanga Jyotishi also discuss solstices, that is Ayanata, and equinoxes, which is Visuva, and uses two intercalary lunar months, which is Adhikamasa, to catch up with the solar calendar. In some ways, this text remains the foundation for India's traditional lunisolar calendar. The early historical period, the second period, extended from 3rd century BC to the 1st century CE and was marked by astronomical computation based on the risings and settings of planets, their revolutions, etc. Jain astronomy also developed in this period based on a peculiar model of two sets of 27 nakshatras, two suns and two moons. It nevertheless resulted in precise calendrical calculation. This is also a period when huge scales of time were conceived of, such a day of Brahma or Kalpa of 4.32 billion years, which curiously comes close to the age of the earth, which is 4.5 billion years. Of course, there are much longer time scales to be found in the Jain texts and in the Puranas. While some scholars have discrete Babylonian and Greek influences at play during this and the next periods, the issue remains open. Nevertheless, such influences seem clear enough in the introduction of the 7-day week in few centuries BCE. Late Vedic India divided the month only into two lunar fortnights or paksha, one light and one dark, and of the zodiac of 12 signs, which is Rashi, first recorded in the Yavana Jataka, that's in 269 CE. The Siddhantic era. There are many gaps in our knowledge after the above period and before the start of what has been called as the golden age of Indian mathematics and astronomy. Beginning in the 5th century CE, this is the Siddhantic era, where texts called Siddhantas were composed, a Sanskrit word meaning principle or conclusion, by which applies here to a collection of conclusion or treatises. Their chief character were the use of trigonometric methods and epicyclic models for the computations of planetary positions. Epicyclic would mean because they were using a geocentric system. Early Greek and Indian astronomers could not explain the planet's occasional retrograde motions as seen from the Earth. They assumed that the planets moved along smaller orbits called epicycles, whose centers revolved around the Earth along larger circles. Aryabhatta I, born 476 CE, working near what is today Patna, ushered in this era with Aryabhatiya, which dealt concisely but systematically with the developments in mathematics and astronomy. Among other things, it discussed units of time and features of celestial sphere, described the earth as a rotating sphere hanging in space, and produced a table of planets' mean positions. Aryabhatta also gave a correct explanation for both lunar and solar eclipses and stated that the diameter of the earth is 1050 yojanas, defining the yojana as 8,000 average human heights or about 13.6 kilometer. This is a close to the actual dimensions through 12% too large. His diameters for the planet and the sun, however, are too small. Many brilliant astronomers followed dealing with the issue of coordinate system, time measurement, and divisions, mean and true position of the celestial and eclipses. Varamihira Aryabhatta contemporary composed in 505 CE a collection of 5 astronomical tests prevalent during his time. One of the 5 texts, the Surya Siddhanta, was revised later and became a fundamental text in the Indian astronomy. Two other expounded the principles of Greek astronomy. Varamihira extensively discussed the revelations of planets, eclipses, and zodiac, often with an astrological background. Bhaskara I, the earliest known exponent of Aryabhatta I, provided a very useful elucidation of Aryabhatta's astronomy besides improved calculation methods. A few years later, Brahmagupta, who lived near Mount Abu, mistakenly rejected Aryabhatta's view of Earth as rotating sphere, but contributed much to calculation of the mean and true longitudes of the planet, conjunction, and problems of lunar and solar eclipses, applying to all these his considerable mathematical skills. Indian astronomers could not have achieved so much without a strong tradition of observation, and the 22nd chapter of Brahmagupta magnum opus and the Brahmasfuta Siddhanta dealt with a variety of astronomical instruments, most of which could be easily made by any good craftsman, among them a water clock, which is ghati yantra, consisting of a bowl with a small hole at the bottom which would sink in exactly 24 minutes. A ghati, if placed over water, a gnomon, a short stick caved vertically for the study of motion of the shadow, a graduated disc or half disc, and a scissor like pair acting as a compass. Those instruments and computational techniques applied to them were both adopted by later scholars beginning by Lalla of 8th century. So here we see the various instruments described by Lalla for astronomical observations. Brahmagupta also authored a manual of astronomical calculation which remained popular for centuries, as testified by Al-Biruni, the Persian savant who came to India in 11th century as part of Muhammad of Ghazni's entourage. Al-Biruni was deeply interested in India's astronomical techniques, wrote about them at length, and translated them by Varahamihira and Brahmagupta into Arabic and Persian. Bhaskara II, better known as Bhaskaracharya, brought important innovations to both astronomical and mathematical techniques, discussing in particular the mean and true position of planets, the triple problem of time, direction and place, and rising and setting and conjunctions of the planets, eccentric and epicyclic theories for their motions of planets, and a large number of astronomical instruments. Overall, Bhaskaracharya greatly improved upon the formulas and methods adopted by earlier Indian astronomers. During those centuries, astronomy's interface with the general public was mostly through calendars and panchangas, which is almanacs, and the prediction of eclipses, which had great religious and social significance. Indeed, an astronomer fame was guaranteed if he could accurately predict the occurrence, nature, and duration of eclipses, and numerous inscriptions record of king's reward to such an astronomer. Another interface was architecture, and many temples show clear astronomical alignments with events such as sunrise at solstices and equinoxes. So here we have one temple, which is the Sringeri temple, whose mandapa is dedicated to the 12 rashis or signs of zodiac. Some of the pillars, they are aligned to the sunrise of the two solstices. Next we have the Kerala school. The widespread belief that there are virtually no progress in India's astronomy and mathematics after Bhaskara II is based on general ignorance of the intense development that took place in the southern state of Kerala. The so called Kerala school of astronomy and mathematics flourished there from 14th to 17th century when networks of knowledge transmission in North India were severely disrupted in wake of repeated invasions. Parameshwara, that is in 1362 to 1455, an author of some 30 works, was one of the foremost astronomers of this school and the founders of the dark system, which improved computation of eclipses and the positions of planets and proved to be very popular. He emphasized the need of regularly correct formulas to bring them closer to the actual observation, and was said to have studied eclipses and their parameters over period of years. He was followed by Nilakantha Somyaji 1444 to 1545, who in his landmark Tantra Sangraha carried out a major revision of the older Indian planetary model for the inferior planets Buddha, which is Mercury, and Shukra, which is Venus, and described them along with Mangala and or Kuja, which is Mars, Brihaspati or Guru, which is Jupiter, and Shani, which is Saturn, as moving in the eccentric orbits around the Sun. This achievement of Kerala School of Astronomy is truly remarkable in the light of the fact that Nilakantha preceded Copernicus, the profounder of heliocentric theory in Europe. It seems unlikely, however, the Indian heliocentrism directly influenced European advances in the field. Other post Siddhantic developments. About the same time, a complex interface with the Islamic astronomy took place, which, among other benefits, brought instruments such as astrolabe to India. The famous and massive Yantra Mantra or Jantar Mantar observatories built in early 18th century by Maharaja of Jaipur Savai Jai Singh represent a convergence between India, Arabic, and European astronomy. In a general way, Indian astronomers were more interested in the efficient methods of computation than in theoretical models. Some techniques used to calculate planetary positions and eclipses yielded remarkably precise results, and impressed by their speed European astronomers such as Ligon Gentil, a French savant who stayed in Puducherry for 2 years to observe a solar transit of Venus in June 1769. All the traditional tables and even calculation methods survived well into the 19th century. The introduction of modern astronomy brought to a close India's own development in the science. But India, in many ways, had contributed to the growth of the new science, as some of the techniques developed by Indian astronomers and mathematicians had been relayed to Europe centuries earlier through the Arabs. Indeed, Indian astronomy interacted not only with Islamic and European astronomies but also with the Chinese astronomy in complex interplays that invariably enriched both players. Thank you.